So before we get started, I think I mentioned this on Wednesday. You will have an online Google quiz due this weekend. It'll open right after class. It'll open at 9:50, and then it'll be due by midnight on Sunday night. It should remind you a lot like what the homework was due on WebAssign last night. Okay, so you'll have an hour to finish it up. You get one attempt. It's a quiz, so you'll get one attempt, an hour to finish it up. Okay, so don't start until you're ready to start it, because otherwise you're only going to have the hour to do it. Right? I don't think it'll take an entire hour. I'm just saying, just don't start it and try to go back, because it won't let you to do that. All right, so that'll be due, like I said, Sunday at midnight. It'll open right after class. All right. Any questions at all over anything before we get going? All right, so last time we talked about combinations of functions. The first part of class, we talked about adding, subtracting, multiplying, dividing functions. And you do that just like you would expect, right? You take the outputs of the first function, outputs of the second function, and add them together if you're adding a function, subtract them if you're subtracting the functions, and so on down the line, right? Then we also talked about composing functions, doing one function and right after another function. So let's do this example. We didn't get to this one last time. Do this example, and then we'll also talk about recognizing compositions and kind of working the other way around. So let's look at this one where we've got f of x is 1 over x and g of x is x minus 1. This problem's asking us to compose the two functions and then again asking us what the domain of the composition is. So again, when we do f composed with g of x, what does that mean again? Yeah, it means f of g of x, right? When you plug in an x, it first goes into g. Whatever comes out of g then goes into f, right? So in this case, g of x is on the inside. What is our g of x equal to? X minus 1. So this problem is asking you to do f of x minus 1. And then again, what does this notation mean? What does f of x minus 1 mean? Good. Plug in x minus 1 for x into the f of x function, right? So what do we end up with? 1 over x minus 1. Good. Not a lot of simplifying to do in this one, but remember when you're asked about finding the domain, make sure that you answer the domain question pre-simplifying, right? We had one last time where if we simplify, we might not have identified the domain correctly, correct? Right? We did this one. When we simplified, we just got an x, and that was like the domain's all real numbers. But remember, this was defined as a composition. It has to go in the square root function first. So when you're asked about domain, make sure that you're always doing it in the unsimplified form first. Okay. Now, like I said, this one doesn't have a lot of simplifying. I'm just reiterating what we talked about last time. Looking at this particular composition now, what can go wrong? Yeah, the bottom cannot be 0, right? When does that happen? When is the bottom equal to 0? When x is 1, so to write the domain, then what would we have? And there'll be a negative 1 to infinity piece. What else? Negative infinity to 1, and then, or negative, or to 1, yeah, sorry. And then use parentheses or brackets. Parentheses, good, because we don't want included, right? So again, we need to eliminate the 1 out of the interval from minus infinity to infinity. What about the second part? What do we do? Yeah, so remember, this is g composed with f, means we do g of f of x. So what are we looking for? And g of 1 over x, right? The f of x in this case is 1 over x, so we really want g of 1 over x. What is g of 1 over x equal to? 1 over x, and then the minus 1's on the end, right? Are we okay with this part? Awfully quiet this morning. We okay with this part? Yes? No? Maybe? Is that right? Okay. Now the second part again asks us for domain. What goes bad here? 0. Yeah, 0 in for x, right? Can't put 0 in for x, because it causes the 0 in the denominator. So what's the domain here going to be? Okay. Okay, 0 to infinity. Good. What questions do you have on that? All right. So what we've done with the composition idea is we were given two functions and asked to put them together. This last page on the handout is basically asking you to break it apart. Look for a composition. This is an important skill later on, being able to recognize what's kind of an inside function and what's kind of an outside function, if you will. So this one says we've got the function f of x is square root of the opposite of x cubed plus 3, and then minus 5 on the outside of the square root. It's asking us to identify an inside function and an outside function is essentially what's going on, right? So what I mean by that is, if I rewrite this as g of h of x, I've got some function with just an x in it on the inside, and then some function where I've replaced the x with that function on the outside. There's no one answer for these, by the way. There's several answers that you might do. But looking at kind of the ideas that we did with transformations. Remember when we did transformations just recently? We looked for that base graph idea, and then look what happened to the base graph. If I were thinking about it from that perspective, what might you use for the base graph in this case? Square root of x, right? So do you think that the square root piece might be the inside or the outside? Just looking at the picture, looking at how the function is described. Do you think it would be an inside or an outside idea? Outside idea, right? Because I'm doing the square root of something, right? It's kind of a big idea. So what if we let our g of x be square root of x minus 5? The minus 5 there on the end, because there's not any x's with it, I'm just putting the minus 5 on the end. Looking at it from that perspective, looking at your g, and then looking at your f, what do you think the x has been replaced with? Yeah, so what do you think we should have let our h of x be then? Yeah, wasn't a trick question, right? Yeah, it looks like the x has been taken out. We put in negative x cubed plus 3 in for it. So that's going to be the inside function. Does it work? If we go through the process of these are our two functions to start with, if we do g of h of x, this is just a check. That says do g of negative x cubed plus 3. That's the h of x that we just said we had. Plug that in for x into the square root, and that literally is what we have, right? That's not the only thing that would have worked, right? There's other things we could have done. For example, you could have had your g of x is equal to square root of x minus 5, or sorry, not square root of x minus 5. Could have done square root of x plus 3 minus 5. If that's my g, what would you use for h in this case? Negative x cubed, right? Because I want to take out the x and put in negative x cubed to make it match what the f is. We could have also done, like I said, there's no one right answer here. What if I let the g be negative x plus 3 and then minus 5 on the outside? What would your h of x be? X cubed, because I already have the negative in there, right? There's lots of different ways we could do it. The idea, though, is recognizing what's on the outside and what's been replaced, what the x would be replaced with on the inside. I think this first one is the more natural way to do it. It's definitely the way you want to think about it later. But there's more than one answer here, as we recognize. Let's do this next one together. We've got f of x is equal to absolute value of 3 minus 1 over x. Let's recognize an inside and an outside again. What do you think the outside function here might be? Okay. Yeah, so that's definitely one case that we could absolutely do. Looking at the outside of this thing, I've got absolute value bars all the way on the outside, right? So I definitely want to have the absolute value bars on the outside. And you said 3 minus x? Yeah. If you make that be your outside function, what would be your inside? What are you replacing the x with? 1 over x. Good. Can you give me another example? All right, you could do it. The plus won't work, but we could do you'd have to have a negative 1 over x plus 3 that way. I would just do it this way. Yeah, but just having the absolute, the outside function being just absolute value of x works great. I just need to take out the x and put in what's on the inside. So we have absolute value of x for your outside, and your inside is 3 minus 1 over x. Either way works. So like I said, there's more than one way to do this. Typically, there's more than one way to do this. Questions on that one? Right. Work on the last one for a minute, and then we'll talk about some new stuff. While you're working on that, I'm going to hand out the handouts for the next section here. Ready to talk about it? This one's a little bit different. It asks you to find 3 rather than 2, right? So you kind of need an overall outside, kind of a middle outside, and then an inside. So what did you come up with? Go ahead.
G of x equals 2 over x.
Okay, I like that one. Why'd you decide that?
Because then it would be easy to put enough x into the square root.
Yeah, exactly. So notice in this case, we've got this thing would be what the x is, right? So what did you come up with for your h of x?
I did h of x equals square root of x.
Okay, cool.
And then j of x equals x plus 4.
Yeah, so you just broke it into 3 pieces, right? That's great. Yeah. So I've got 2 over something, right? The something happens to be a square root of something. And then the final inside piece is that x plus 4. That works great. So what others came up with? Maybe come up with something different.
Should you put the square root first on g of x?
If you did the square root first, how would you get rid of the square root on top? What did you do in the next step then?
I did the h of x is x plus 4, and then I just put the j of x is 2 over x. But yeah, I don't.
Yeah, so that would, I think you would have an issue because then your 2 over x would be inside your square root. So another way you might do it, like I said, there's more than one way to do this. What if I started with g of x is 2x? What might you use for h then? 1 over, 1 over square root of x, or 1 over x will work, either or. If I do it 1 over x, square root of x, what would your j of x have to be? It'd be x plus 4 again, right? If you did that, what would your j of x have to be? Square root of x plus 4, right? Because I need that square root of x plus 4 to go on the bottom. Okay. Again, like I said, there's somewhere I have to have a reciprocal in there to make that square root of x plus 4 piece to be on bottom. In the first example here, the reciprocal was done as the outside function, so then that next inside function needs to be the square root, because I need to put the square root on the bottom, right? If I don't make my reciprocal on the outside, then I've got to do it on the inside. So when you replace the x with 1 over root x, I've got 2 over the square root. I would still need to put in the x plus 4 on the inside. In this one, I've got 2 times something. I've got the reciprocal of something. Now I have to put that whole square root of x plus 4 piece in the denominator. In this last one, you might see that you might be able to break it up into 4 pieces, right? I could add 4, because the 4th piece, if you wanted to do it that way, you could have something that looked like this. And this kind of gives you the idea of what would you have to do if you actually plugged in a number for x, right? If I plug in a number in for x, what's the first thing you're going to do? If I plug in a number for x, what was the first thing you have to do? Add 4. So that's why I can make my inside function be x plus 4. The first thing I do is add 4. What's the next? After you add the 4, what's the next thing you do? Do the square root, right? So that'll be the next inside function. What's the next thing you would need to do? Well, my square root is on bottom. I need to take the reciprocal of it, right? So that's my next inside function. And then finally, we multiply that answer by 2. So you can think about breaking it into 4 pieces if you wanted to. Again, like I said, there's no one right answer to these. There's several right answers to these. What questions do you have on any of these 3 that we just did? As you've probably learned before you've gotten to this class, a lot of things in math ask you to put things together and tear it back apart. Right? You've done factoring before. That's tearing it back apart, tearing multiplication back apart, right? That's essentially what we're doing here, right? We've talked about putting functions together and then tearing them back apart again. All right. Well, let's go on to the new stuff, which talks about one-to-one functions and inverses. So the idea of inverse is to be able to undo things that you did. It's kind of like I just mentioned a minute ago. Put things together or tear it back apart, right? So if we want to do inverses, we're trying to undo whatever operation that we did, if we can. So that's the idea of inverses. To get to inverses, we need things to be one-to-one, which is why that is the first definition that we have here. So what we mean by a function is one-to-one, I'll say it in words and then I'll write it in symbols. If it's one-to-one, that means if you put one thing in, functions are if you put one thing in, you get one thing out. If I put a different thing in, if it's one-to-one, I have to get a different thing out. So what we say in words is that distinct inputs yield distinct outputs. Said another way, if I put 2 different things in, I have to get 2 different things out. Okay? The way to think about it in words. If I put 2 different things in, I have to get 2 different things out. So in notation, we would say if x1 is not equal to x2, then f of x1 is not equal to f of x2. The x's are your inputs. This says 2 different inputs, distinct inputs. If I put different things in, if it's one-to-one, I have to get different things out. Okay. That's our definition of one-to-one. Different things go in means different things come out. Sometimes you'll see this written the other way around, which is known as the contrapositive. The contrapositive says that if the same thing came out, then you must have put the same thing in twice. Notice that the statement is flipped around, right? That's the contra part. The contrapositive part means that you flip the negation around. So we flipped which is the consequence and which is the hypothesis, if you will. We flipped the second statement and the first statements around, and then we negated each of them. That's what we mean by contrapositive. Logically, they say the exact same thing. All right. So let's look at this first example where I give you an example. Well, I give you a set of ordered pairs. So let's review a little bit Remember, for a function, we need to look at what? If I have multiple outputs for the same input, right? That's vertical line test idea. Is this a function? Do you see multiple outputs for the same input? No. So this is a function, right? So now we ask the other way around. Is it one-to-one? Do I see the same output for different inputs? Yeah. So here's input 1, output 3. Do you see another one that has an output of 3? Yeah, the 4, 3 right here, right? So this is not one-to-one, not a one-to-one function. And again, if I write this in function notation, this says that f of 1 is the same thing as f of 4 because they're both equal to 3. So I found two different inputs that gave me the exact same output. Okay? So let's look at this next example where I give you an explicit function definition, and I also show you the graph. Is that function f of x equals x squared minus x minus 2, is that one-to-one? Do you see two different inputs that give you the same output? Looking at the graph, do you see two different inputs that give you the same output? Yeah. Can you give me two of them? Just looking off the graph. Okay, good. So this is the point -1, 0, right? You see another point that that you can plug in to give you 0? 2, 0, right? That's the point 2, 0. So looking at the graph, f of -1 is equal to 0 and f of 2 equals 0. And certainly, -1 is not equal to 2. So f is not one-to-one. It's a very good observation there. Yep, exactly right. So notice that this function crosses the x-axis twice, which means that there are two different numbers that you plugged into the function and gave you 0. Does that make sense? What about the next example at the bottom there, where we've got x cubed minus 1? Do we see two different inputs that give us the same output here? Notice above, the reason why we had two inputs that gave us the same output was in particular that x-axis crossed the graph twice, didn't it? Notice that there are other, well, like maybe I draw the line here at y equals 2. That tells me there's two different numbers that would give me 2 out, right? You see it? This down here would tell me there would be two different numbers that give me -1 out. Using that same idea down below here, how many times does that line cross? Just once, right? And this one, just once, right? As we move up, those horizontal lines only cross one time. Okay? So in this case, we would see that f of x is one-to-one. And we're looking at that graphically. And we use this idea of looking at horizontal lines crossing the graph. So notice that the horizontal lines would, if it crosses the graph twice, that means we're getting at least two outputs that, at least two inputs that give you the same output, right? Because that horizontal line would be all those places where the function has that particular output. Like we said up here with the x-axis, right? We had those two outputs, those two inputs that gave us 0. So what we're using here is what's referred to as the horizontal line test, which is what I have labeled here on the top of the next page. The horizontal line test says that a function is one-to-one if and only if every horizontal line intersects the graph of the function at most once. Okay. So we have two different line tests that we learned now. The first one we had was our vertical line test. Vertical line test is used to determine whether or not a graph represents a function, right? Do we have two outputs for the same input? This is kind of the flip around of that notion, right? Do we have two inputs that give us the same output? So that's horizontal line test. Right. So that'll be our big test to know whether or not we have a one-to-one function or not. The reason why we care about one-to-one functions is so that we can talk about undoing them. So what I mean by that is, if I go back up here to this function, I'm going to erase all these extra little lines I put in here. See it a little bit better. If I go back up to this function up here, if I tell you 0 came out, are you 100% certain what went in? If I say I plugged in a number, I got 0 out, are you 100% certain what specific number I plugged in was? No, because I have two possibilities, right? So when you don't have a one-to-one function, you can't undo it easily. Okay? This is why we care about the ideas of one-to-one functions. One-to-one functions are allowing us to understand whether we have this idea of being able to undo something. If I look at the second example, if I tell you that I got -1 out, can you for certain tell me what I plugged in? What did I plug in if I got -1 out? 0. If I tell you that I plugged in, or I got out 0, can you for sure tell me what I plugged in? 1. Yeah. So I can undo that one, right? For certain. That's what we want to be able to talk about when we talk about inverse functions, all right? So when we define the inverse function, it's defined as we have y equals f inverse of x, and I'll talk about this notation here in a second, is defined as y equals f inverse of x if and only if f of y is equal to x. So this is how we define the inverse function. Notice what happens. The y is what went into the original function. The x came out. It's been flipped here, right? So inverses interchange your x's and your y's, right? You're used to plugging an x in, you get a y out. We're trying to reverse the process. We have what the output was. What was the input? Okay, that's the idea here. All right. So how do we do this to find inverse functions? What steps do we use to find this? And then we'll play around with it. All right. So notice that we just said that the x's and y's get flipped around for inverse functions, right? Inputs become outputs, outputs become inputs, okay? So the first step that you're going to do is flip-flop. We're going to change all the x's to y's. Oops. And all y's to x's. Okay, that's the first step. So wherever we see a y, and there'll only be one place we see a y, and we'll see that here in a second. Everywhere we see a y, we're going to write x instead. Everywhere we see an x, we're going to write y instead. The next step will be solve for y. That's step 2. And then step 3 is we'll replace y with the notation f inverse of x. Now, be careful with this notation. This is very, very important. This notation does not mean flip f upside down. Okay? This is not a negative 1 exponent. Okay? If I want to flip f upside down, I actually have to write f of x, the whole thing written to the negative 1 power. Okay? This notation means find the inverse function. It does not mean flip the function upside down. Okay? It's very, very important to remember that. All right. So let's see if we can find the inverse function for this first example that I have here. The first step we're going to do, and notice that remember we think of f of x as the y. So I'll make y equals 5x minus 2. The first step again is to flip-flop your x and y around. So we now have x equals 5y minus 2. And now solve for y. What do we need to do to solve for y? Yeah, add the 2 and then divide by 5. So that is our inverse function. Now that's the last step, is rewrite it as f inverse of x equals x plus 2 over 5. Before we go on to the next one, I want to chat just briefly about this. So a couple of things. Let's look at the original function. If I plug a number in for x, what's the first thing you're going to do? Multiply and then subtract, right? If I'm going to undo that, I got to undo the subtraction first, because that's the last thing that I did, right? So I got to undo the subtraction, which is addition, and then we undo the multiplication, which is division, right? It's not unlike when you put your socks on and then put your shoes on. What do you have to do first to undo that process? Your shoes and then your socks, right? Try to take your socks off, you're going to put a hole in your sock. Right? That's not the right way to undo that operation. So it's the same idea here. So notice that we subtracted 2 last. That's the first thing that we undid. And then we multiplied by 5. So that was the next thing we undid. The second thing I want to mention is that we didn't look at this and verify that we actually had an inverse before we started. Remember, the way we verify that we have an inverse is that the function has to be 1-to-1. And we just said that we did that through the horizontal line test looking at the graph, right? So looking at this particular function, in particular looking at this form that I wrote it in, what kind of graph would you see if you graphed this function? A line, right? The slope of that line is 5. So the line would go like that, right? Does that graph pass the horizontal line test? Yeah, sure it does, right? Because it's only going to intersect every horizontal line one time. So we definitely have a 1-to-1 function here. Questions on that one before we go to the next one? All right. Let's do the next one, next couple here. Pardon me. First thing we're going to do is write this as y equals 1 minus 2 root 2x plus 5. What do we do next? Yeah, flip the x and the y, right? Make y's x's, make x's y's. So I get x equals 1 minus 2 root 2y plus 5. Now what do we do? Yeah, solve for y, right? So what do we have to do first? Oh, so I got a 1 minus 2 times something, right? So what do I want to do with the 1 first? Yeah, let's subtract it. And then what? We can divide by the negative 2 is perfectly fine. Yeah, square both sides. Good. So now we have x minus 1 quantity squared over 4. I just went ahead and squared the negative 2 as well. Equals 2y plus 5. Then subtract 5. And then finally, divide by 2. So at the very end there, we get x minus 1 squared over 8 minus a 5 halves. I could, if you really, really wanted to, you could multiply out the x minus 1 squared and get a common denominator. Do you think I care if you do that or not? No, good. Right answer, I don't care. And then finally, the last piece we have here is that this is the inverse function. Any question on the process there at all? Yes.
What is that next to the x minus 1 over 2?
That's squaring both sides.
Okay, where does the squares come from?
Hmm?
I said, where does the squares come from?
I'm trying to undo a square root, so I need to square both sides to undo the square root. So that was actually a question I was going to ask. The original function has a square root in it. Are you surprised that a square pops up in its inverse? No. Right? Because squaring and square roots undo each other, right? At least to some extent. I'll have a little bit of a discussion about that later. Right. Let's look at this next example. Not that this is the end-all, be-all of all inverse types of functions, but I can guarantee you that you will see one of these on a quiz and you'll see one of these on a test. Okay? Well, as your homework, but I'm telling you, you're going to have to know how to do this type of thing because the skill involved that to be able to do this type of problem does pop up later. Okay. All right, so again, make our y equal to 4x plus 2 over 3x minus 6. What's step 1? Flip the x's and y's. So we get x equals 4y plus 2 over 3y minus 6. Now I need to solve for y. That's the next piece, right? What do you think you might want to do first to solve for y? Say again? So how can I simplify? What would I need to do to simplify? Or what can I do to simplify? What don't you like about this? There's a plus on top and a minus on bottom. In particular, we have a fraction, right? Any way to get rid of the fraction? Yeah, let's multiply both sides by what? That's probably a good idea. Yeah, I'd do that first. Right? Multiply both sides by the 3y minus 6. Because that gets rid of the 3y minus 6 in here. What do you think we might want to do next? Good, exactly right. We need to get the y's on one side, right? Remember, we're trying to solve for y. I need to isolate the y, right? Right now I've got y's on both sides. I need to put them all on one side. To be able to do that, what do you think we should do first? Say again? If I divide by x, I'm still going to have an issue. I think I'd rather do something else besides divide, because I already cleared a fraction. Rather than divide by the x, what do you think you'd rather do with that x? I'd rather distribute it through, right? So I don't introduce the fraction until I have to. 3xy minus 6x equals 4y plus 2. Again, we're trying to isolate the y. So what do you think we should do next? Well, I want to isolate the y, though, right? I got y's on both sides. Yeah, I'll take the 4y over to the other side. And if I want to isolate the y, what do you think you want to do with that 6x? Add it to the other side. Good. Remember, we're trying to isolate the y, right? If I want to isolate the y, I need to get all the y's on one side. What does that allow us to do now on the left-hand side that we couldn't do before? Take the y out. It's a dirty 6-letter F word. It's factor, right? I need to factor the y out, don't I? Y times 3x minus 4 equals 6x plus 2. Now, finally, to be able to solve for y, what should we do? Yeah, just divide. Exactly. Just divide by the 3x minus 4. Again, like I said, this is not the end-all, be-all of all inverse functions. The idea, though, of being able to isolate the y when you've got it on both sides is a skill that's going to pop up later. Which is why I said that there will be one just like this on a quiz and just like this on an exam. What questions do you have about this one? All right. So to remind, we'll finish talking about this next time as well as get into the next section. Just to remind, at 9:50, your quiz will open up on Moodle, right? It's due by midnight on Sunday. Once you open it, you have an hour to finish it, okay? All right. Have a good one. We will see you on Monday. Have a good weekend, everybody. Very good.